At over 1,500 miles long, the Himalayas are home to some of the tallest mountains in the entire world. And in this remote region of Nepal sits the tallest of them all, Mount Everest, standing at a mighty 5.5 miles high. And to help us understand how on Earth such a colossal mountain was formed, geologists need to get their hands on some rock samples from its peak. But considering the harsh landscape and freezing temperatures, how do scientists get up close and personal with the world's most famous mountain? And what lengths would they go to in order to grab a slice of that rocky pie? To answer these burning questions, we joined forces with National Geographic and some brave adventurers to find out how a team of experts scaled the world's tallest mountain to retrieve vital rock samples. The story starts at Everest Base Camp, which sits at 17,500 feet. This is the starting point of many climbers' journeys to the top of the world. But our intrepid explorers were setting off on a slightly different kind of expedition. They needed to reach the summit of Everest to grab some geological samples. So on April 2005, they began their 55-day hike. It might not sound too strenuous, but considering they're essentially walking uphill for pretty much the entirety of the journey, it's safe to say there were some tough times ahead. The first leg of their journey took them through the Khumbu Icefall. Here, steep glaciers carved by the movement of the two tectonic plates, the Eurasian and the Indian, hang ominously over the valley floor. As you can imagine, climbing this particularly treacherous stretch of land proved quite difficult, and it wasn't just because of the steep, slippery terrain. You see, the entire area is made of glacial ice, which is constantly shifting and moving. This means that what looks like a sturdy ice tower one moment could collapse the next. And if you happen to be anywhere near it when that happens, then you're in big trouble. After 4 days of carefully making their way through the icefall, our explorers reached Camp 1 at 20,000 feet. Here they had a bit of a breather before tackling even more challenging landscapes. But just how dangerous was this icefall that our team had to cross? It's actually one of the most dangerous parts of the entire mountain due to the constant threat of ice avalanches. In 2014, an ice tower collapsed at the icefall, causing an avalanche that swept down the mountain. It destroyed 3 ice bridges and killed 16 Sherpa guides who were helping other climbers ascend the mountain. But anyway, after taking a well-earned break at Camp 1, it was time to move on. The team set off through a relatively calm part of the mountain, passing by Western CWM or the Western Saddle before reaching the next camp. Camp 2, which sat at around 21,000 feet. From here, the team were greeted by some spectacular views of the mountain and surrounding areas. Looking back, the Western Qum stretched below them while the path ahead snaked upwards towards Camp 3, which sat precariously on the edge of the Khumbu Icefall. After some rest and recuperation, the team prepared themselves for yet another dangerous trek. They knew that the route ahead led straight into the heart of the Khumbu Icefall. It was time to face the danger head-on. After about 3 hours of trekking, the team arrived at Camp 3. At 24,000 feet, it's one of the highest camps in the entire area. And it was here where the team had to contend with temperatures as low as -22 degrees Fahrenheit. That's about -30 degrees Celsius for our friends in the metric system. And to put that into perspective, that's about the same temperature as a popsicle. The team had to spend about a week here getting used to the altitude and the freezing cold conditions before continuing their mission. Now, while it's not the highest camp on Everest, it is one of the longest standing. Due to its location on the southeast ridge, it's the closest camp to the dangerous icefall. But it's usually still in use when teams start to descend the mountain. After getting their bearings, it was time to continue their quest for samples. But before we go any further, why don't you tell us in the comments how high you think Camp 4 is? Go on, take a guess. We'll wait. So the team packed up and started the final ascent to the DeathZone, located at 26,000 feet. This is also known as the South Col. Getting to this point in the journey is no mean feat. In fact, some expeditions have to turn back at this point simply because the altitude is too much for them. Others don't make it this far due to the extremely unpredictable weather. Storms in the DeathZone can easily turn a pleasant day into a raging blizzard in a matter of hours. Add to that the freezing temperatures and the thin air, and you've got yourself a potentially lethal combination. And that's not forgetting the oxygen. At lower altitudes, there are around 27,000 oxygen molecules per liter of air. But at 26,000 feet, that number drops to just 9,500 oxygen molecules per liter of air. This makes breathing significantly more difficult. There's only one reason why people push themselves to endure such harsh conditions, and that's because the death zone sits just below the summit of Everest. Once they'd reached Camp 4, the team only had about 2,000 feet left to climb. With that in mind, they had to spend several days here acclimatizing to the lack of oxygen. This gives their bodies a chance to adjust to the thinner air by producing more red blood cells and boosting their lung capacity. The last thing the team wanted was for someone to suffer altitude sickness midway through the final stretch. Now, while the team adjusted to the altitude, we thought we'd take a moment to talk about the person leading the expedition. Kenton Cool. Kenton is a professional mountaineer and an author from Northumberland, England. He has summited Mount Everest a record 9 times, but he didn't stop there. He's summited all of the 7 summits, the highest peaks on every continent. In fact, he was the first person ever to summit Everest in the winter. He's certainly a man who knows his stuff. Okay, now back to the adventure. After some much-needed R&R, it was finally time to scale the last stretch of the mountain. Kenton and his team knew that they only had one shot at this. If the weather took a turn for the worse, or if anyone in the team wasn't feeling 100%, then they'd have to abandon the mission. With supplies, food, and extra clothing, each team member was laden with almost 80 pounds of equipment. And that's before you factor in the additional weight of the oxygen tanks that they needed to stay alive. Despite the weight of their packs, the team set off towards the summit, leaving Camp 4 behind. Their goal was to reach the Hillary Step, which sat just 400 feet below the summit. In the early hours of May 2005, Kenton and his 2 Sherpas, Ang Dorje and Ang Shearing, made it to the top. The Hillary Step. It was here where Kenton got to work collecting rock samples. But as he and his team scrambled around the summit, looking for suitable specimens, they noticed something. The rocks that they were scrambling over were completely different to the type of rocks that they were expecting. The summit of Everest is composed of a rare type of granite called orthoclase granite. But the rocks that Kenton was looking at were dacitic. Dacitic is a volcanic rock that's usually created under high pressure deep beneath the Earth's surface. It's rarely found above ground, let alone at the top of the world. In fact, this particular rock should have been thousands of feet beneath the surface. So what happened here? Well, according to Kenton, the piece of rock that he was standing on was originally a magma chamber that filled with molten material. Over time, the magma solidified into a giant dome of dacite. When the Indian plate began to rise upwards, the massive slab of rock was pushed up with it, eventually poking out of the ground. But that's not all. While the team were up there, they also discovered some small pebbles. These pebbles were composed of a shiny black mineral called coesite. Coesite is typically found in metamorphic rocks that have been exposed to high levels of heat and pressure. But how did these rocks end up on the roof of the world? While Kenton collected samples, his team prepared to return to Camp 4. The descent was almost as perilous as the ascent. But eventually the team made it back to the relative safety of their camp. Although they hadn't gathered the samples they originally planned on, they did manage to bring back some very important discoveries. Back at base camp, the samples were examined by geologist Steve Pravec. Steve was amazed by the unusual composition of the rocks and decided to conduct some tests to try and figure out what had happened here. He discovered that the rocks were pushed up from between 6 and 9 miles beneath the Earth's surface. They were formed due to the intense heat and pressure caused by the collision of the 2 tectonic plates. But Steve was particularly interested in those small pebbles of coesite. He had never seen anything like them in Nepal before. And that's not all. After analyzing the samples further, he discovered that the rocks originated from deep within the Earth's mantle. In fact, they were so old that their origin point had been identified as part of the Australian plate, which was part of the supercontinent Gondwana. Gondwana broke up millions of years ago, but evidence of its existence lives on in the rocks at the top of Everest. Thanks to the hard work of the climbing team and the geologists, we learned a lot about the history of Everest. But what happened to the samples after the analysis was complete? Well, some of the samples were sent to the Natural History Museum in London, while others found a home at the National Geographic headquarters. As for Kenton, he went on to summit Everest a few more times. In fact, he was at the Hillary Step once again in 2019. Sadly, though, he had to turn back, just 200 feet from the summit due to bad weather. But that doesn't mean that he's given up. We don't blame him. After all, there's nowhere else on Earth quite like it. Now, you need to watch how Mount Everest will look in 100 million years. Have a look at this.